Hi, everyone. I'm Tristan Arbus. I'm a data scientist for Devon Energy Corporation in Oklahoma City. I've titled this presentation, Is This Thing On? Which in this case refers both to the well state model that I've created, which is designed to determine whether or not a well is in production, currently running, as well as to non-data scientists working closely with data science models and wondering, is this thing even working right? The goal here is to solve both of these issues, the technical problem and the people problem. So this is one of my favorite quotes and one that I use to guide my project philosophy. People ignore design that ignores people. Frank Chimera is not a data scientist. He's a designer, one who works in media. So think branding, books. He's the type of guy you might call up to make you a new company logo. So while he obviously wasn't thinking about data science when he penned this, I think it holds true for anything that's people facing, including applications in data science and their end users. In the case of this particular project, we had to take careful steps to make sure our processes, models, and results were digestible and usable by engineers and techs, which I'll talk a lot more about along the way. So with that, here's what I'll be covering. First, in order to better understand the problem and why we care, I'll talk a little bit about what production is exactly. Then I'll discuss how we came up with a solution that promotes usability and adoption. And I'll close out by talking about the good, the bad, and the ugly about what we did. So before all that, this right here is the first thing that you, your end users, clients, so on and so forth, should be asking when starting a data science project of any kind. What is your goal? And your goal should guide how you approach the problem from the beginning. So what's more important, model accuracy or model readability? Does it need to be understandable? Whose buy-in do you need? How will you get it? The answers to questions like these can prescribe certain model types, certain processes, or methods of deployment. In the case of this particular project, we need to make sure we come up with a solution that is understandable, as accurate as possible, and ideally is immediately usable by engineers and field personnel without additional software equipment. So keeping those goals in mind, let's start talking a little bit about exactly what production is and what we're here to solve. Production, simply put, is the phase of a well's life cycle where we're extracting hydrocarbons. By the time a well gets to production, a huge investment has already been made, and it's not until we gather our product, essentially, that we begin to profit. It's also the phase of our well that lasts the longest. Typically, fracked wells have some sort of artificial lift system to aid in hydrocarbon extraction. There are many forms of artificial lift, such as gas lift injection or electric submersible pumps. But for this project, we decided to initially focus on rod pumps due to a controller that provides a readily available supervised learning data set. So basically, in order to extract oil and gas, the beam system rocks back and forth, operating the string of rods below. These work similarly to the pistons inside a cylinder, converting the reciprocating motion into vertical fluid movement, and thereby lifting oil from the reservoir through the well up to the surface. And for the sake of this project, it's not incredibly important to understand exactly how everything in this diagram works. Just a very basic understanding that we're dealing with certain gas rates and pressures suffices just fine. So let's take a look at those. This is an example of just some of the parameters we received from the field. It's displayed on a time scale. So here we're looking at various pressures and gas rates over about a 1 month period. Choke differential pressure is the difference between the pressure at the pump jack and the backside of the well. Total gas rate is pretty self-explanatory. It's the rate of gas leaving the wellbore. And tubing pressure is the pressure within the production tubing string, which you can think of as the outside shell of the piston. These parameters are going to form the backbone of our model. In this screenshot, we actually have two fairly distinct shutdown events labeled as periods of off. While they look pretty obvious in this context, this is an idealized case. They're not all that simple or clean, and we do need some sort of model that's more than just some simple threshold. I also want to talk a little bit about why we want to know when we're shut down. There's some obvious reasons. One being, if your rod pump is offline, you want to get it back online. If we're not making money when we should be, that's a bad thing. A better understanding of when we're shut down or not will also help our reporting and give us a better understanding of our rate of production while online. And also, we'd like to be able to optimize production while online and learn more about predicting shutdown events before they happen. So in order to do this, we first need to know when we're shut down and when we're not. This is, of course, keeping in mind that we have thousands of wells in production at any point in time, and it would be impossible to manage all of this manually. Like I mentioned before, thankfully, and for myself included, we don't really need to understand exactly what these parameters mean to a production engineer. What we need to do instead is work closely with production subject matter experts, our SMEs, to get a better understanding of what we might expect the parameters to do during a shutdown event. So what you're looking at here is the initial whiteboarding session during which exactly that was discussed. We were able to hone in on the fact that certain parameters should drop to zero, even if they don't always. Certain parameters should get quiet, which would lead to maybe analyzing the standard deviation or the range. And certain parameters would be rising or falling, which means we may want to analyze the slope. This is all to say that something as simple as a whiteboarding session like this with an SME can lay critical groundwork before modeling. The architecture used to get production data from the field and into the hands of our engineers and technical personnel is also a critical factor in how we approach the problem. Each device in the field is attached to a controller which communicates wirelessly with a supervisory control and data acquisition SCADA system. The data is then organized and stored in our Pi asset framework, the Pi AF, which acts as a hierarchical, asset-centric repository for our data. I have it circled here because the Pi AF is going to act largely as the linchpin for data access and model deployment for us as well. It has a built-in analytics engine and is also where people already go for all their production data needs, exposing that data via real-time alerts and or surveillance tools and dashboards similar to some of the screenshots I've already shown. Oil and gas is definitely an industry where an additional piece of software, one window, or just an additional mouse click or two can act as a barrier to adoption. So the closer we can bring our models to the existing systems, the better. I mentioned this earlier, but I want to talk about the controller for a second. Rod pumps are somewhat unique in that they output a run status from the controller that tells us whether we're running or shut down. What this means for us is that we essentially have a baked in supervised learning data set. We can tell our model where we're shut down for it to learn from with some level of confidence. So why are we trying to solve a problem that already has a controller telling us the answer? There are a few reasons. Like I mentioned, rod pump is unique. And while we have about 750 wells operating with rod pumps, we have closer to 6,000 wells operating on other lift types for which we don't have a supervised learning data set. So if we can prove the ability to recognize shutdown events, our SMEs can be convinced to manually comb through some data, designating shutdown events by hand, and creating that supervised learning data set for us for other lift types. Without some sort of proof up front that it works, could be difficult to get that sort of time and commitment. So here's a less idealized example of what our data might look like, as well as some solutions to the issues we see. Because of ratty data, we'll want to perform some sort of smoothing. In our case, done via simple moving averages. We can deal with missing data by defining certain data quality filters that can check that parameters are within expected ranges and are currently communicating. Pi can help us deal with variable data frequency innately as it interpolates already, meaning if we ask Pi for a data point every 15 minutes, it will automatically do that as long as we check for data quality. And lastly, it's important to recognize that we have multiple parameters we want to analyze, but we don't want our model to fail if we're missing just one, which is extremely common. Taking this into consideration, we chose to go ahead and make multiple models, one for each parameter separately, and combine them in the end, depending on how many accurate parameters we have at the time with good data quality. Pi System Explorer is where we did a lot of our backend work. Here we can perform calculations on existing parameters, normally referred to as attributes of Pi, and output new attributes using the built-in calculation engine. So here, first we set up a new attribute to check for data quality by checking for bad values and making sure that there have been enough events that we're still getting communication for that parameter. Then we calculate the basic statistics again. Like I mentioned, a moving average, slope, a standard deviation, and a range. These will now conveniently live within the PyAF along with all of our other parameters for easy access and can act as inputs to our models. So at this point, we could very easily make a simple trigger using the same calculation engine that says something to the effect of, I expect my well to be shut down if my differential pressure is quiet. So I'll take a guess and say that I'm shut down if my standard deviation is less than 5. We could easily program that alarm directly into the PyAF, but to me that's like sticking your finger to the wind to check for direction. You can probably get close-ish, but for sure there's a better way to do it. Better tools, better methods, and ideas exist. So instead of sticking our finger into the pool of data and taking our best guess, what can we do? Decision trees are the answer. After all, they're just large sequences of if-then statements anyway at their core. Hopefully they can hit that sweet spot we're looking for between accuracy and understandability, and we should be able to figure out how to get them back into the asset framework. First, we need to get our data out, though. Most people familiar with Seek utilize it as a visual data analytics processor where you can search, process, cleanse, find patterns, etc. It can connect to a number of databases, including in our case, the PyAF. And we do use it for that sometimes. However, there's also a little something called Seek Data Lab, which allows us to utilize Seek as a data grabber that can pull data from the PyAF to Databricks through Seek. So here we're just using dbutils to install the Seek library, import the spy function, and use it to connect to the Seek database. And from there, it's as simple as searching for assets along your well's path, grabbing the assets you want to request, and pulling them. Here I'm pulling a few parameters on a 15-minute interval over the course of about a month and a half. In reality, for modeling, I would also be pulling all of our calculated data quality and statistical parameters and pulling over a much larger time frame. With that in mind, here's our modeling workflow within Databricks. We'll import our data and filter it based on data quality, like already mentioned, perform a training and validation split and oversample the training set, do some basic hyperparameter tuning before performing a grid search and training our final tree. And then finally, to solve our deployment issues, we'll export the final tree as code that can be interpreted by the Asset Framework's analytics engine. We already discussed how we import and filter our data, so let's jump right into talking about the training validation split. I initially tried a basic 80-20 training validation split using 80% of the data to train and 20% to validate the model, but ran into issues with generalization. So in an effort to increase our model's ability to generalize across an entire field of wells, we asked our engineers to choose our validation set for us. That is, we asked them to determine a set of wells that, in their mind, if the model works on those wells, it will work everywhere. We asked for the validation set to span everything they typically see as far as varying data quality and parameter availability goes. This sort of manual validation set selection proved to perform way better than even more quote-unquote advanced techniques such as k-fold cross-validation. This is simply a case where our subject matter knowledge is superior to randomness, which not only helps the model to generalize, but helps the engineers and end users to gain more knowledge, influence, and ownership over the modeling process, which is going to help with overall understanding and adoption. One of the biggest hurdles to overcome is that we have an imbalanced data set. In fact, 5% or less than 5% even of our data represents wells in a shutdown state. Typically, a few methods exist to deal with such an issue, including undersampling, oversampling, and weighted classes. I ended up using the synthetic minority oversampling technique, or SMOTE. In case you're wondering, because I did have to look this up, SMOTE is the past tense of smite, but we're not talking about divine punishment for our data. Now, the SMOTE process is part of the imbalanced learning Python package and allows us to create new synthetic data from which to train. What you're looking at here is an example of how SMOTE would work on a 3-class classification problem where the yellow class greatly outnumbers the teal and purple classes in the original data set on the left. By applying SMOTE to the data set, we can achieve something like what's shown on the right, an oversampled data set with new samples that mimic the distribution of samples in the original data. There are a number of different algorithms within SMOTE, mostly based around which algorithm is used to identify samples to consider during resampling. For the purpose of well state, We ended up using SVM smoke, which is a version that uses the support vectors from a support vector machine algorithm to create new samples. To find the ideal parameters for our decision tree, we can do a grid search, which we will do, but first we should find some good starting points. One way to do this is by iterating on one parameter while keeping all the other parameters default and checking your model accuracy. Our chosen accuracy criteria is AUC, which stands for area under the curve. It represents the probability that a random positive sample is ranked more highly than a random negative sample. And a higher AUC means a more accurate model. As mentioned earlier, we're going to make a different model for each parameter and its statistics. So we're going to want to run this process for every set of inputs. And here we see the results for keeping all variables except for tree depth constant for our differential pressure and total gas rate based models. And it looks like the training and testing AUC diverge in the 8 to 12 range for both, which means in order to prevent overfitting and maximize accuracy, something in that realm might be a good place to start our grid search. And we can repeat this process for all of our other decision tree parameters. So that's exactly what I did. And then we performed our grid search. So here you can see the best and worst results of what I would consider to be a brute force grid search performed on our parameters. I iterated on the columns seen here. Shown here are the top and bottom performers. And we chose this method of grid search mainly to gain some greater clarity into the benefits of adding depth to our trees, as well as so we could harvest the best parameters for trees at different depths. The reason for that was because we wanted to start with smaller, more understandable decision trees. So if you handed this image to an engineer who's familiar with production, it's easy for them to make sense of the decisions that are being made. So to follow these decisions, you just start at the top of the tree and follow it down. In this case, the first choice we make is our tubing pressure range less than 7? If it is, we go to the left. If not, we go to the right. Whatever box we end up in tells us if we're more likely to be shut down or running. So if we were to follow the logic down the left half of the tree, you might say something like, if my range is low and my standard deviation is low, I'm shut down. The lower my standard deviation, the more confident I am about that. If my standard deviation is a bit higher, but my tubing pressure is low, I'm probably still shut down. But if my tubing pressure is higher, I can't really be sure. And honestly, that's really good. The ability of our end users and engineers to understand exactly how a model is making its decisions is extremely important. However, remember our most accurate trees were something in the realm of 7 to 10 splits deep. And we still need to figure out how to get these back to the pi AF. So luckily for us, as mentioned earlier, decision tree is really just a sequence of if-then statements. So this Python function here is written to comb a decision tree for its features and print out code that can be copied and pasted into the pi AF. Essentially, we've written some code to write some code. The function requires only 2 inputs, the tree object and the feature names. It takes the feature names and performs some text formatting, and then recurses through the tree, printing if statements for each internal node. Once it gets to a leaf node, it utilizes the Gini value of that node to calculate the probability that the well is shut down at that leaf. Thus, we're able to output exact if-then statements you would follow to make decisions based off that tree. I should note that we could probably write these if-then statements ourselves in about 10 minutes from just looking at the tree, but that's not where the major benefit for this function comes in. This is where it comes in. So if you remember earlier, the ideal depth again was about 10. So good luck writing code for this guy. But with our custom function, we can easily get the code on the right to paste into pi. And something that I want to stress here is not just the scalability of the code, but the scalability of the idea. We chose decision trees as our model of choice for a few reasons. One of which was to give increased insight and understanding into the model structure and decision-making process. There's only a relatively small conceptual jump to make from understanding a small readable tree to a larger one. And that understanding into our model garners additional trust and buy-in, all important things that our solution needs to have. It's also worth mentioning that our increase in accuracy isn't that high when making a deeper tree, in this case, less than 1%, but that's fine for a few reasons. First, it's an increase all the same. And according to our hyperparameter tuning, we're not overfitting, so that's okay. Second, it offers increased granularity. So while the actual designation of running versus shutdown hasn't increased in accuracy much, those decisions are now spread across many more leaf nodes with a much wider range in our Gini and purity values. This means when we run the model and view our percent chance for shutdown, we'll be able to assess with more insight into the model's confidence at any point in time. And lastly, in this rare case, I'm okay with the tree being big for the sake of being big. We're not sacrificing accuracy or overtraining, so we have an opportunity for our end users to utilize a model that they can understand but can't necessarily read. And this paves the path to other potential models in the future that may have less understandability and an increased trust in the data science process as a whole. So here you can see the code pasted back into our Pi environment, and based on the coloring, our Pi is parsing out the code exactly as we like. The only thing we did was add a data quality check on top to make sure we only execute the model when we have appropriate data quality. So let's take a look at how our model performs on the shutdown event we looked at earlier. Here we have our parameters and our 2 shutdown events circled. Again, you can see the run status controller triggers a shutdown. Right below the run status, we have our models. We have a tubing pressure model in blue, a delta pressure model in purple, a total gas rate model in red, and an average of all of them in yellow. You can see most of the time our combined model floats in the 40 to 60 range, not really exhibiting much confidence in anything really, until we get to a shutdown event where it climbs up dramatically, making it extremely easy to recognize. Below the models, on the bottom trace, we have something called event frames, which are a function of Pi and consist of some backend logic running on our models that allows us to boil things down to event level and recognize and query periods of downtime that we would consider to be a shutdown event. You might notice that the red total gas rate model is often flatlined at 40. Our total gas rate model ended up being less reliable, and therefore we combined it with a heuristic approach, allowing the model to run only sometimes. This slide is mostly just to show you that I'm not cherry picking examples. This was a screenshot essentially capturing one moment in time for all of our rod pump wells where we trained our model. On top, they're sorted by those with lowest shutdown confidence, and you can see they're all running according to the controller. Below, we have wells with the highest shutdown confidence, and most, but not all of them are shut down according to the controller. So overall, the model is performing well on a macro scale, but let's talk a little bit about more when the controller is wrong. Here we have an example when our models actually outperform the controller. Again, I have our shutdown event circled, and it may be a little hard to read, but the run status controller is actually outputting a status of run. However, looking at our parameters and going based off of our subject matter experts and knowledge, we're clearly shut down. The model recognizes this and very easily creates an event frame that recognizes the shutdown event, showing that even after training on the controller-based supervised learning data set, our models can now even outperform the controller in some cases. So with this proven out for the next phases of the project, we'll be moving on to training similar models for other types of lift that don't have a controller. Now that our end users can see and understand how the models work and perform in a production environment, there's motivation to put in the work up front and create a supervised learning data set. And we're working on those sorts of things now. As with most data science projects, there's always room for improvement. Firstly, and largely beyond the scope of this particular project, is the data quality and improvements in data collection. The better our data set is up front, the more likely we're able to get information out of it. I would have liked to spend a little more time feature engineering. While I sort of teased about putting our finger to the data wind and choosing random thresholds for a manual approach, that's kind of what we did with features. We took some base level statistics and ran with them as inputs into the model. I believe the models would benefit from some additional time exploring and engineering the inputs. And my last 2 bullets here sort of go hand in hand. There are model types that can outperform decision trees and that I would like to utilize. But our choice to use decision trees was based off other factors such as readability and ease of deployment, and I believe was the right decision. But now that we're starting to get that buy-in, we may be able to move on to more complex models and deployment solutions in the future. Because yes, deploying a decision tree as code in our Pi system is not very long-term friendly. We run into issues with performance tracking, potential model updates, so on and so forth. And so as we have some great stuff in production right now, we're still figuring out the best ways to support it and transition it into a more future-proof solution. So just a quick thank you to the engineers, IT support, members of the analytics team, and others who've worked on this project with me, to the Spark AI Summit for having me, And also thank you for all of you for listening and watching. I've really enjoyed working on this project and being a part of the conference. So again, thank you.